Hello and welcome to Histology 101. I'm Jamie Chapman. I'm your host, taking you through the slides that no one wants to look at, but you're forced to look at as being a student of histology. So today we're going to be focusing on the histology of cartilage and bone, and particularly looking at bone growth as well. And then in the second half, we're going to be having a look at the histology of the liver, the gallbladder, and the pancreas. So this is actually covering two main areas. One for our first year medical students who recently did histology of those, the bone and cartilage with me. And then for the second years, it's sort of a catch up on those systems, the end of the alimentary tract. So that's the liver, gallbladder, and pancreas. And then next week we'll be having a look at the histology of the urinary system, which is what we looked at this week. So if you're around, please keep an eye on my Twitter, and I'll announce when that live stream will be. Okay, so we're going to start off first. In the first half of this stream, we'll be having a look at the histology of cartilage and bone. So we're going to start with the histology of hyaline cartilage. Hyaline cartilage is the most abundant type of cartilage in the human body. It forms a large part of the wall of the respiratory system. So we can find it in some of the external nose structure, and then the rest of the respiratory system down to the levels of the small bronchi, and then it stops at around about that level. It's also found forming the early model for endochondral ossification. So our bones, our long bones that form through endochondral ossification actually start out as a hyaline cartilage model, and then eventually they get replaced by bone through a method called ossification, and we may talk about that in this live stream. So hyaline cartilage is characterized by, let's move forward. Let me go to the wrong button. No, it's not working. Okay, there we are. So we're going to actually have a look here. This is a section of the trachea. So this is actually here, the hyaline cartilage actually forms these nice C-shaped ring structures. This structure here is the esophagus, which sits on the posterior surface of the trachea. So this is anterior. This is posterior. So we have this C-shaped, quite pale staining basophilic structure here, and this is the cartilage ring, the hyaline cartilage ring. So if we zoom in here, we can actually begin to see some of the structure. It's relatively sort of pale basophilic in appearance, so this sort of pale purple in staining. And then we've got this thick layer on the outside and a smaller layer on the outside here. So it's kind of like a hyaline cartilage sandwich, if you like. Now, the bread of the sandwich is actually made up of an important layer known as the perichondrium. Peri means around and chondrium refers to cartilage. So the perichondrium is this layer that surrounds the outside of the hyaline cartilage. So it's actually made up of two layers. It doesn't look like that on this side, and that's because it's sort of continuous with the connective tissue underlying this epithelium here. This is respiratory epithelium. And here it's sort of a bit truer representation of what we sort of consider the perichondrium. It's made up of an outer fibrous layer, which consists of this dense irregular connective tissue. So these are big thick bundles of collagen here, and then these nuclei belong to fibrocytes. And remembering fibrocytes are the predominant cell type that we find in dense connective tissue. They're sort of the mature form of connective tissue cells, and so they're responsible for the maintenance of this extracellular matrix out here. What we can see here too is we can actually see some blood vessels, and that's his primary role of the, or one of the roles of the perichondrium, the outer fibrous layer, is actually to bring blood supply and provide nutrition and remove waste for the hyaline cartilage, because hyaline cartilage itself, if we have a look at the matrix here, we can see there's actually no blood vessels. So it's actually, we consider it sort of avascular in the sense that there's no blood vessels within the matrix itself. So they're actually found in the outer perichondrium. So we can see a little blood vessel here, and we can see some more over here as well. There's another little one here. So that's the outer fibrous layer of the perichondrium. So it helps to bind the cartilage ring to surrounding structures. So we've got some adipocytes out here. So this is some of the adventitia on the outside of the trachea. So the connective tissue binds it to this perichondrium here. And then the second layer, which is closest to the matrix of the hyaline cartilage, is known as the inner chondrogenic layer. So chondrogenic means, chondro, that prefix refers to cartilage, and genic means genesis, so the origin of cartilage. So here we actually have these flattened cells. These are actually stem cells that can actually differentiate and form new chondroblasts, which are the immature form of the cell type that makes up cartilage matrix. And so when we have those sort of differentiation, we've got blast versus site. The blast cells are responsible for the synthesis and the secretion of the extracellular matrix in connective tissue. The site cells are those that are responsible for the maintenance of that extracellular matrix. So they're the sort of mature form. So the blasts tend to have a cytoplasm that typically displays lots of rough endoplasmic reticulum, lots of expanded cistern of the rough ER, because they're actively synthesizing the collagens and the glycosaminoglycans and the proteoglycans that make up the extracellular matrix, which is this sort of material on the outside here. So these cells, the chondroblasts, these are the ones that are going to be found more towards the periphery of the cartilage itself. So the more sort of rounded ones here that we can see, these are going to be the chondroblasts, and then the ones which are sort of more central here with the slightly darker nuclei, these are the chondrocytes. So the chondrocytes in cartilage, because the matrix is a semi-rigid structure, it's quite a rigid structure, they're actually trapped within these little holes within the cartilage matrix, and these little holes are known as lacunae. And lacunae means little lake, and so these chondrocytes and chondroblasts down here too are trapped within these little holes called lacunae, and they sort of sit there and they're able to maintain this extracellular matrix. Now I suppose you might ask, if we've got blood vessels out here and there's no blood vessels here, how do these cells actually get their nutritions and how do they get rid of their wastes? Well, if we think about the actual composition of the extracellular matrix that makes up the hyaline cartilage, it's actually predominantly water. About 70 to 80% of the volume of cartilage matrix is actually water. Hello, 6:40 a.m. Dr. Shio, greetings from Vienna. Guten Tag, Guten Morgen, I should say, because it's 6:40 in the morning. Thanks very much for coming in and dropping by. Hello, thanks very much for coming along. It's really great to have you here. It's great to have an international audience, so thank you. So as I was saying, the extracellular matrix here is predominantly made up of water. 70 to 80% of the volume of the extracellular matrix is water, which means that it's actually a very good diffusion medium. So actually the blood supply here can diffuse its nutrients through, and these cells, the chondrocytes within their lacunae here, can actually receive their nutrition. You might notice slightly different sort of appearance in staining between this matrix here and this one here. You can hopefully see it's a little bit sort of this sort of paler, less blue kind of stain. It's almost like a slight pinkish almost colour. And then once it's out here, it's the more mature sort of purpley stain. That's because these cells here, these are actually making the new extracellular matrix. These are the chondroblasts, the newly differentiated chondroblasts from the chondrogenic layer of the perichondrium. And so they lay down new matrix and they actually widen the matrix from the outside. And this is a special type of growth that cartilage can undergo. There's sort of two main ways in which cartilage can grow. This way that we're talking about here is a type of growth known as appositional growth. Appositional growth is where you get differentiation of a stem cell from the perichondrium into it forming a new chondroblast, and then that chondroblast begins to secrete a new extracellular matrix. And so eventually that extracellular matrix grows and those chondroblasts eventually get trapped into the middle of the matrix and they become the more mature chondrocytes. So this matrix here, because it's newly formed, stains slightly differently to the more mature matrix. Now, the matrix, as I mentioned, is predominantly made up of water. It also has proteins, and the most predominant protein in hyaline cartilage is a type of matrix, type of collagen known as type 2 collagen, and that's specifically the predominant fiber type in hyaline cartilage. So each different cartilage type, there's 3 different cartilage types. We have hyaline cartilage, elastic cartilage, and fibrocartilage. Each of those cartilage types actually has its own type of dominant fiber type. So hyaline cartilage has type 2 collagen. When we get to elastic cartilage, it of course has elastic fibers as their predominant fiber type. And when we look at fibrocartilage, it actually has type 1 collagen as the predominant fiber type. I think that's pretty much it. So some of the other features, I like these cells on this side actually. These are a little bit more flattened, but I do like these. I think they're really lovely, nice round, newly formed. They look like little baby chondrocytes to me. So that's why I think of them as chondroblasts, like little baby chondroblasts formed from the mesenchymal stem cells here. So you can see how they sort of transform into this more rounded appearance. Now, every now and then what we might see are these little accumulations of chondrocytes or chondroblasts in the same lacuna. Now, this happens when we undergo the second type of growth that's possible within cartilage. Now, it predominantly happens during fetal development, but it may happen after, if in response to growth or damage, repair, and that's known as interstitial growth. Interstitial growth is actually mitosis of existing cells. So we end up with 2 cells trapped within the same lacuna, and then eventually they both secrete extracellular matrix so that the lacuna actually separates into 2 individual lacuna rather than the 2 cells being in the same lacuna. So that type of growth, as I mentioned, is known as interstitial growth, and often we end up with this grouping of chondrocytes forming what's known as an isogynous group. Now, isogynous groups just means that they all originated from a single cell, and then they've divided and probably divided again. Eventually they'll all secrete extracellular matrix and generally separate from each other. But sometimes you can actually see them really close together, something like this. You know, you get these cells very close together, and obviously they've undergone mitosis and they've begun to secrete this extracellular matrix to separate them within the lacuna there. So I might just zoom out a little bit here, so we can actually see the ends of the cartilage here for the C-shaped cartilage ring. You might notice here that the posterior region of the trachea has this smooth muscle layer. This is known as the trachealis muscle. I know this isn't... are there any chondroclasts in the tissue? Look, that's a term which I see pop up every now and then, but I've never really identified chondroclasts myself. So that's something which I actually need to spend a little bit more time investigating about the features of chondroclasts and how to identify them. I don't typically describe them when I talk about the histology of cartilage to our students. It's a really good question, and it's something which I need to spend a little bit more time on. If you've got any tips, Dr. Shio, about how we actually identify chondroclasts, please let me know. If they were like osteoclasts, then they're really easy to identify because they're big multinucleated cells, and I've never seen anything like that with cartilage. I don't know if you have anything to add. So we've got Dr. James Crane sitting off to the side here, falling asleep, listening to the histology, as probably most people do. So he's here to point out if I miss a chat question and so on, and he can moderate the chat should there be a need. No worries, Dr. Shio. Thanks for the question. I'll try to have a look that up, and maybe in the next stream I'll make reference to it. Or I'll tweet about it. How about that? I'll tweet about it. So if you can follow me on Twitter, then you can keep track of that. It's a really good question, actually, and something which we might pose to our anatomy, ask an anatomist question. I think that's quite a good group. So for anyone who follows or goes onto Twitter, there's there's a hashtag called EnactQ, and if you go and type in a question into Twitter using that hashtag EnactQ, then a number of anatomists around the world actually follow that hashtag, and they'll answer you, help you find the answer to your question. And we have a number of histologists there. I Heart Histo, LL Cool Prof, which is Dr. Lisa Lee, and a number of other histologists are out there helping to answer your question. So that might be a good one to post there. So if I can't find the answer, we'll definitely put the Brains Trust to work on Twitter. Okay, so does anyone, assuming anyone's out there, have any questions relating to the histology of hyaline cartilage? So this is in the trachea. Obviously it's quite large structure here, as I say, forming this C-shaped ring. What I thought I might do is just, I thought there must be cells consuming the matrix for turnover, otherwise the exponential growth would just thicken the cartilage further and further and further. Yeah, absolutely, that's a really good point. I don't know if there's a massive amount of growth that happens through appositional growth, but you're probably right. There's obviously part of the role of when we talk about maintenance, we talk about a fibrocyte or a chondrocyte or an osteocyte maintaining an extracellular matrix. Some of that does actually involve resorption. So it actually, in the case of osteocytes, they can actually perform the role of both an osteoblast and an osteoclast. So they can secrete matrix or they can actually digest matrix. And so part of that maintenance is actually part of that role of the mature cell. So maybe the chondrocytes play part of that role. I don't ever see anything that looks like it's actually actively endocytosing or digesting hyaline cartilage matrix, but I haven't spent a lot of time looking for it, but they're not as obvious as you might think about, like osteoclasts. So those are very big, very prominent cells. It's a really good point though, and something worth investigating. This is just another section of, I thought this is a nice one actually, looking at the trachea here. You can see it's not formed a nice C-shaped ring. We've got actually a couple of levels of hyaline cartilage here, but there are sort of some interesting some features here. So if we have a look at this, and again I think I'm talking to the void, but if we think, how might we classify this epithelium? What do we think this type of epithelium is? Is it a simple or a stratified epithelium? So the way to tell, stratified, Histo101, thanks very much, great. Yeah, it is a stratified epithelium, and then we can tell largely because we've got this lovely layer of basal cells. So a stratified epithelium will always have this layer of basal cells down the bottom here, because these are the stem cells and they're going to undergo mitosis, and then one of those cells is going to migrate up, and these cells actually lose their contact with the basement membrane. Whereas we know a simple epithelium actually all sit on a basement membrane. And so they have quite a different appearance here. So these cells are all held together by lots of tight junctions, and we can actually see nuclei all the way to the top, and you can see that these nuclei are very flattened. So we would actually classify this as a stratified squamous non-keratinized type of epithelium. So this is actually the esophagus, which in humans is lined by that type of epithelium. And then over here we've actually got the cartilage. Here's the hyaline cartilage. So here's our outer perichondrium out here. Here's our main matrix, and so here's our chondrocytes within their lacunae. So this is the matrix out here, and then here we've got our perichondrium with our outer fibrous layer of dense irregular connective tissue, and then our layer of inner chondrogenic layer, these sort of flattened cells here, forming these new chondroblasts. So this is just showing we've got some glands down here as well, but it's got quite a thick, nicely well-developed outer fibrous layer of the perichondrium there. We've actually got a little bit of an infiltration of white blood cells in this blood vessel here. See them sort of accumulating here. All right, so the next slide is a section of the lung. And so I just wanted to point out, remembering that it's actually found throughout the respiratory tract, right down to the level of they stop at the level of the bronchioles. So here we've got a nice bronchus. We sort of zoom in here. So here's our epithelial lining. It's actually got some mucus on the surface here. You can actually see it coming away a little bit here. There's a little bit of layer of smooth muscle here. We've got some glands out here, but then we've got these little hyaline cartilage plates. So rather than forming the C-shaped rings, which we saw in the trachea, within the bronchus of the lungs, we can see alveoli out here, so we're obviously within the substance of the lung itself. The hyaline cartilage is restricted to these hyaline cartilage plates. And again, we've got our chondrocytes within their lacunae amongst the matrix. And we've got our perichondrium on the outside there. So that's on that side. There's another one on this side as well. You can see this little plate here. You can see a couple of blood vessels, another little plate here. If we sort of zoom out, maybe we can actually see some of these others. There's no cartilage there. We can zoom around and often we can sort of find evidence of cartilage or not if they've been replaced. You can see all of this now is all alveoli, and so therefore there's no cartilage present in these outer parts here. Again, there's no evident cartilage in these larger ones here. So you can see it disappears fairly quickly. Once we're in the substance of the lung, the cartilage disappears, and we end up more with a larger smooth muscle structure to these larger conducting airways, or these smaller conducting airways, I should say. All right. Okay, so that was hyaline cartilage. The next type of cartilage we're going to be having a look at is elastic cartilage. Elastic cartilage, like its name suggests, is a very flexible type of cartilage. The classic region where we find it is our external ear, and it gives it its ability to deform and then reform, spring back into shape. And that's because of the abundance of its protein within its matrix, and that is, of course, the elastic fibers. Now, under normal H&E staining conditions, it can be difficult to distinguish a section of elastic cartilage from hyaline cartilage. So this is the epiglottis. Now the epiglottis is part of the larynx. It's sort of when you swallow it closes over the larynx and prevents food and fluid moving into the lower parts of the respiratory tract. So it actually sort of has quite a flexible little lid, like the lid of a rubbish bin, I guess. You know, when you step on that step and it flips up and then closes over again. So it has quite flexible core of elastic cartilage. So this is what this material is here. Now, this is actually best visualized using a stain specific for elastic fibers such as orcein. And so our next slide is actually a section of the esophagus, which has been stained with orcein. Now, orcein stains elastic fibers black, and so you can see all of this black material in the matrix of this elastic cartilage. So if we sort of zoom in here, you can see all of this sort of hairy-like material out here. These are all the elastic fibers being stained by this orcein, and then these holes, of course, are our lacuna with our chondrocytes on the inside. Out here, we've got the perichondrium. So elastic cartilage has a perichondrium, so it can undergo both interstitial and appositional growth. And you can see sort of this origin of these elastic fibers sort of extending down from what will be the outer fibrous layer of the perichondrium and extending down into the matrix itself. I think it kind of looks kind of cool seeing all these elastic fibers, and it's so dense obviously that this material accumulates this stain very, very densely in the matrix itself. So we'll go to the other side. We'll see if any difference in appearance. Again, we've got our outer fibrous layer, and then here's our newly forming chondrocytes. And you can see that the density of the fibers here aren't as dense as in the mature matrix. So the fibers start off as individual fibers, and eventually they form these more bundled fibers of elastin. Now we also find a high predominance of water in the matrix here. We also find collagens as well. Wherever you find elastins, you typically find collagens, and they help to sort of restrict overstretching of elastic fibers. So they're always concurrently occurring together. And again, being secreted by the chondroblasts and maintained by the chondrocytes. So this is the, as I said, the epiglottis, and we can find it in the external ear as well as a sort of typical sites for location of elastic cartilage. The third type of cartilage is a type of cartilage known as fibrocartilage, and as its name suggests, it has lots of dense fibres. It's predominantly type 1 collagen, which is a very strong type of collagen, the most abundant type of collagen and the strongest of the collagen types in the body. So this is actually a section here of the spinal column. So out here we've got the vertebral bodies. Here's the spinal cord, and then this is the spinous process of the vertebrae. So if we, whoops, I didn't mean to do that. What I meant to do was this. So if we think about the structure itself, we've got our body of our vertebra sort of occurring here, and then we have this gap, and then we have the spinous process on the posterior surface. And so then in between, we have our intervertebral disc. So this is our intervertebral disc here. Okay, and so here's our spinal cord, and this is our spinous process, and this is the body of the vertebra. So our lateral transverse processes will be sort of coming out of the screen at us, if you like. So the intervertebral disc is made up of two components. It's made up of this annulus fibrosus, which is the hyaline cartilage part. And then this here is the nucleus pulposus. Now the nucleus pulposus is sort of this gel-like substance that sort of acts a little bit like a ball bearing. So if you think about the intervertebral discs, and it gives it a little bit of a rotational feel to it, but it's also that rotation is sort of resisted by the dense fibers of the fibrocartilage. Now, what happens is if you actually rupture your intervertebral disc, in particularly the annulus fibrosus, you do have the potential for this gel-like substance of the nucleus pulposus to actually move out to wherever the tear has happened. Now, often this tear may happen laterally or it may happen posteriorly, and of course if it happens posteriorly, you may get a bulge, a disc bulge, pushing out onto the spinal cord and causing pain. Something like sciatica is a typical sort of example of where you can get the disc bulge pushing out onto the spinal cord there, and it can cause obviously a lot of problems. So if we get rid of that then, and we go back to this, so our annulus fibrosus, as I mentioned, is where we're going to find our fibrocartilage. Now we can actually also see here some examples of bone. So we've got some spongy bone here, there'll be some compact bone out here, and we've got these growth plates. So this is actually taken from a developing animal. So these are actually, growth plates are actually made up of hyaline cartilage as well. So we've got some hyaline cartilage here. This is some developing bone. But here we've actually got our fibrocartilage. This is a trichrome stain, so collagen has been stained blue, and you can see how blue this tissue is. It's actually lots of thick bundles of type 1 collagen, and then spaced in between we have these lacunae, not the nice round lacunae like we saw in the hyaline cartilage, or the elastic cartilage, but more flattened because of course it's lots of fibers and they have the potential to squish the lacunae here. So here's our chondrocytes sitting within the lacunae within this fibrocartilage. You can see them sort of in these rows here. Now fibrocartilage is often thought about as being sort of an intermediary between hyaline cartilage and dense connective tissue because of these abundance of bundles of collagen fibers, providing a very strong structure. So we find fibrocartilage where we want just a tiny little bit of flexibility. We don't want the same density as bone. We want a little bit of flexibility, but we want to resist most forces. And so obviously we don't want our vertebral body separating, because of course then that leads to paralysis and other sorts of problems. And so we find it in areas where we want nice strong bind but a little bit of flexibility. So the intervertebral disc is one example. The temporomandibular joint is another example. The menisci of the knee to prevent sort of that extra rotation of the femur on the tibia. And the pubic symphysis, so that joint between the two pubic bones at the front of the pelvis. To resist separation, we've got a little bit of flexibility there, but very, very strong connection holding those bones together. So again, it's the composition of that extracellular matrix which will determine the functional properties of that connective tissue. So in fibrocartilage, type 1 collagen bundles means very, very strong tissue. Elastic fibers means elastic tissue. Hyaline cartilage has predominantly water, so it's a nice sort of cushioning effect, but also a semi-rigid structure as well. So in the case of the respiratory system, it's about keeping the airways open. Okay, well, I think that pretty much covers the histology of cartilage. Unless anyone has any questions on the chat there, we can begin our look at the histology of bone. I'm just looking at the time here. We've got about half an hour left to discuss the histology of cartilage and bone. There's obviously a bit to get through. So if there aren't any questions, I'm going to have a mouthful of coffee. So let me just pop off the screen for a second. And I'm back. All right, so let's move to our next slide then. If we're going to, no questions about the histology of cartilage, we're going to move on to the histology of bone. And this is a section here. The reason I put this one in next is because this actually has examples of 2 of the 3 types of cartilage. So this was to finish off the cartilage discussion. So hyaline cartilage, as I mentioned, can be found in the respiratory system as well as the developing bones. And we can actually see evidence of this in this line here. But it's also lines the surfaces of bones and forms what's called articular cartilage. So if we have a look here, this is, I should go back to put you into context. This is the femur. And this is the knee joint, stained with trichrome again, so blue is collagen. This is the tibia, and here's the fibula down here. And here's the menisci. So there's one part of the meniscus here, and there's another part down here. So this is the joint of the knee joint. So we can see the space, the joint space here. And when we zoom in, we can actually see some of the synovial membrane, which helps to provide the fluid for this joint cavity. Now, in terms of hyaline cartilage, it's quite a unique structure, articular cartilage. It sort of it's a remnant of the original model of the bone that actually began growth. So if we think about endochondral ossification of our long bones, it starts off with this hyaline cartilage model, and eventually what happens is that we get these little ossification centers, and it starts off in the shaft of the bone, and that forms the primary ossification center. So the shaft of the bone gets replaced. We get these secondary ossification centers forming in the heads of the bone, known as the epiphyses, and they sort of form these explosions of bone in each of the 2 epiphyses, the proximal and distal epiphyses, and we get these zones of remnant hyaline cartilage from that original hyaline cartilage model. And the remnant part forms the articular cartilage on both surfaces, and then also forms this other structure here. If we sort of zoom down, this little band of tissue, this is known as an epiphyseal growth plate. So we have these sort of 4 bands of remnant hyaline cartilage. We've got the proximal articular cartilage, we've got our proximal epiphyseal growth plate, and then we've got our 2 distal growth plate and articular cartilage. So we've got these 4 zones of remnant hyaline cartilage. Now, articular cartilage is unique amongst the other types of hyaline cartilage in that it doesn't have a perichondrium. So we can see there's no outer dense fibrous layer like we saw in the trachea, and there's no fibrous layer here because actually this is spongy bone. This is actually newly forming spongy bone here. So here's the delineation between the bone matrix and then the hyaline cartilage matrix, which is forming this articular cartilage. So this means then that remember when we talked about the C-shaped rings of the trachea, that the perichondrium played a really important role in allowing diffusion of nutrients and wastes from those blood vessels within the outer fibrous layer of the perichondrium. But because articular cartilage doesn't have a perichondrium, it can't actually use those blood vessels to provide nutrition. So the way in which it does that is actually relies on this tissue here, which I was mentioning before. And this is the synovial membrane. And there's another part of it here. You can actually see that it forms this enclosed cavity. So here's our joint cavity, here's our joint space. And this tissue here, this is the synovial membrane. The synovial membrane is a connective tissue layer that has lots of capillaries within it, and it actually provides the serum transudate, the sort of plasma part of serum, into the space like this material here, and this bathes the surfaces and provides a diffusion medium through which we can actually supply nutrition and remove waste for our articular cartilage. So this synovial membrane, which we can see here, is providing nutrition for our articular cartilage. Now, the fact that it doesn't have a perichondrium also means it doesn't have an inner chondrogenic layer, so it actually can't undergo appositional growth. It actually needs or can only undergo interstitial growth, which is a slower method of growth, meaning that we can't get fast differentiation of stem cells to form new cartilage cells, new chondroblasts. So the only way that articular cartilage can repair is through interstitial growth, through mitosis, and it's a much slower process. So this is our articular cartilage. I'm sorry, some of this section is a little bit of out of the plane of section here, so a little bit of artifact there. But this is our matrix, and here's our chondrocytes forming this articular cartilage. So the other reason I wanted to point this out, now this is a section of the knee joint from a cat. So cats being quadrupeds means that they don't put all of their weight on two joints like we do as bipeds, like in the knee joint in humans. So their menisci is actually not purely fibrocartilage like it is in humans. So we can actually see that this part of this wedge-shaped structure here, which is forming the meniscus within the knee, is actually hyaline cartilage. But if we go down, we can actually see the matrix begin to change. We get these bundles of collagen. And so that when we reach this part of the meniscus, this is actually fibrocartilage. Okay, so out here we've got hyaline cartilage, and then we get this sort of transition from hyaline cartilage to fibrocartilage. And hopefully you can see that quite dramatic change in structure of this matrix here. So from this material that doesn't look like it's got much going on here to the more fibrous material, these bundles of collagen running in different directions. So this is our fibrocartilage of our meniscus. So for those students of mine who were looking at this section and having difficulty interpreting it because that looks like that, you know, because it's actually hyaline cartilage, but it's the base regions here which are the fibrocartilage. And we'll see that on the other side as well. Again, we've got our hyaline cartilage. You can see how similar this tissue here looks to the articular cartilage here. Interestingly, what looks like happening here is we've got a little bit of ossification happening. So this looks a little bit like a primary ossification or a secondary ossification center, which is really odd. Like, it's not something which we see in humans. But we've definitely got bone formation happening here. So we actually have osteocytes. These are osteocytes. This is the newly forming bone tissue here. So for some reason in the calf, in this section, this region of the meniscus is undergoing ossification. It's a really odd thing. But we still have our fibrocartilage, which is the sort of typical tissue that we see here. Anyway, sometimes that happens when you do a little bit of comparative histology. Sometimes we see things which we don't normally see in humans, and it gives us a little interesting point of reference to compare and contrast between the different organisms that we're looking at. Some nice blood vessels here, so we can zoom in, can see a nice little artery here. So you can see this little wavy line. For those of you who remember the histology of the blood vessels, this is known as the internal elastic lamina, which is typical appearance of a muscular artery. So this red tissue here, this is our smooth muscle. So here's our tunica intima, which is made up of the endothelium layer of loose connective tissue, which is very small in the internal elastic lamina. Then we have our tunica media, which is smooth muscle, and then our tunica adventitia on the outside here. Here we've got a vein, small muscular vein. You can see it's much more irregular in appearance. We've got our endothelium here. We've only got one layer of smooth muscle, and we've got lots and lots of blood cells trapped within it there. Again, we've got another vein on the side here. Anyway, that was a little bit of offside. Not exactly something we were discussing particularly. This is a really lovely section. I really love this section, and I love showing this section because it's so bright and vibrant, and it's also got some very interesting things going on with it. So we're going to move to our look at bone. We are running quickly out of time. Of course, there's two major types of bone in adult bone. This is compact bone, which is predominantly found within the diaphysis, or the shaft of the bone, and the outer surfaces, sort of like forming the shell of the bone. And the second type is known as spongy bone or cancellous bone, or trabecular bone, and we saw some evidence of that in that previous slide. So we zoom in here. This is trabecular bone or spongy bone. It's characterized by having these irregular shapes, and it's sort of made up of these several layers of bone tissue known as lamellae, but the difference being that there's actually no blood vessels within the inside of the spongy bone here. Whereas if we have a look at this section, this is a section of dried bone. All of these little openings are little openings for blood vessels to reside. Because of course the difference between cartilage and bone is that the bone matrix is mineralized, so actually diffusion doesn't work through the matrix of bone. So they actually rely upon blood vessels within their structure themselves. Now they do it in a very unique way compared to most connective tissue cells. Now most connective tissue cells are widely separated by the extracellular matrix, and they don't have any connections with each other at all. And they rely upon diffusion through that extracellular matrix. Now, bone tissue, because it has a mineralized extracellular matrix, means diffusion doesn't work through that extracellular matrix. So they overcome it by forming a network within that matrix, but the cells make contact with each other. And this is the unique part of bone as a connective tissue. The fact that the cells actually have cell junctions between them. They have gap junctions between long cytoplasmic processes, and that they form this network, so that if we have if we zoom in here, we can imagine that the blood supply is within this structure here. This is this circular arrangement of bone tissue here is known as an osteon, or a Haversian system. On the middle here, this here is called the Haversian canal, and lining this Haversian canal is a layer of tissue known as the endosteum, and there we find the blood vessels. So here, these little dark spaces, these represent the lacunae of bone cells. So we had lacunae in cartilage, we have lacunae in bone. The difference being, of course, that the matrix is mineralized. So you can see these little legs, these little extensions. They almost look like ants or spiders. And these long spider legs or ant legs are actually little canals within the mineralized bone matrix. So these are actually known as canaliculi. And so they actually have long side of these osteocytes which sit within the bone. These lacunae have long cytoplasmic processes which extend out to the blood vessels and make contact. So they're able to get their nutrients. Infiniteness Lives asks, where is the cell boundary? Well, this is actually dead tissue. So the lacuna, if we do a little bit of a zoom in here, we zoom that in. So the cells actually die during processing for this type of microscopy. So the cell would exist within this lacuna here, and then these little canaliculi, the cell membranes, would run within there. So the little cytoplasmic extensions would exist within these canaliculi. But we generally refer to this space as the lacuna, and we expect that the osteocyte would fill that space. So I'm hoping that's what you were referring to when you're asking about the cell boundaries there. So this osteocyte, for example, makes connection with the blood supply, and then this cell, you can see it's quite far removed from the blood supply. So how does this get its nutrients? Well, this cell actually makes connection with the cytoplasmic processes of this cell, and they have gap junctions. So this cell can pass on the nutrients to this cell, it can pass on the waste, and so on. So we have this network of cells amongst this mineralized matrix. So these these bones form these rings of bone tissue known as lamella, and so within an osteon they're known as Haversian lamella, and they form these circular rings, and at the junctions between the lamella we find the lacunae, and then you can see these little canaliculi running in, and as I said, this space is the Haversian canal, and this would normally be lined by endosteum, which is a layer of tissue made up of osteoblasts, osteoclasts, and osteoprogenitor cells, but also carries blood vessels within it. So this is what we're seeing. So we're seeing lots of these osteons. Interspersed between the osteons, we actually have old remodeled osteons, and these are known as interstitial lamella. So they sort of form the spaces in between the osteons. So anything out here, for example, this is interstitial lamella. The ones around the Haversian canals, these are actually known as the Haversian lamella or concentric lamella. We might see some of these sort of lateral openings here. So we actually have sort of two canals which exist within compact bone. The ones that are in the middle of the osteons are known as Haversian canals. The ones which sort of bring the blood vessels from the periosteum this time. The periosteum is a layer on the outside of bone, compact bone. From the outside of the periosteum to the inside of the bone are known as perforating canals or Volkmann's canals, and so these are also lined by endosteum. So remember previously we talked about I'm just going to zoom out here. Previously we talked about cartilage have a perichondrium. Well, bone has a periosteum, and it has two layers just like the perichondrium. So it actually has an outer fibrous layer. Sorry, we'll wait for it to catch up. So here's our compact bone. This is like where you can actually see the nuclei of cells here now. This is the outer, this is the periosteum. So just like the perichondrium, it has an outer fibrous layer consisting of dense irregular connective tissue, and then it has an inner, instead of chondrogenic layer, it has an osteogenic layer or an osteoprogenitor layer. And rather than containing just purely osteoprogenitor cells or stem cells, it also is the site for osteoblasts and osteoclasts. So this is one of the main sites for finding osteoblasts and osteoclasts. So we can see the blood vessels out here. This is the outer dense irregular connective tissue of the periosteum, and then the osteoprogenitor layer are sort of the cells which are found on the surface here. Here, this is the cartilage matrix. Now, when we actually section living bone, we very rarely actually see those lovely sort of circular osteons and so on. When we do see these openings, these are some of the perforating canals and then the Haversian canals which exist within this cartilage compact bone matrix. Now, this bone is still undergoing development. So what we're seeing here, this is actually old cartilage matrix. So this pale blue region is this old cartilage matrix, and it's eventually being replaced by this bone tissue. So this is part of that endochondral ossification, the replacement of the cartilage matrix model by bone cells. So these flattened cells here will be part of the osteoprogenitor cells. You can also find osteoblasts and osteoclasts. This large cell, very acidophilic cell, this is actually an osteoclast. So this is, you can see the little sort of depression on the surface here that it forms. So the osteoclasts sit within those sort of depressions. The more rounded cells would be the osteoblasts, whereas the more flattened ones are the progenitor cells here. Okay, and they line all the internal surfaces as well. So when we think about the two tissue types, the periosteum and the endosteum, really the endosteum, which lines all the internal surfaces, is basically an extension of the inner osteoprogenitor layer on the insides of the bones. So you can actually see one of these canals here, and we can see the lining tissue. So this is the endosteum lining this canal here. Some of this is going to be the Haversian canal, and then this is going to be the perforating or Volkmann's canal. So just remembering that if you see a longitudinal section of compact bone like this, anything running sort of in a perpendicular perpendicular way to the length of the bone is going to be a perforating or a Volkmann's canal. Anything running lengthways with the bone is going to be a Haversian canal. So this I'd classify as a Haversian canal, whereas something like this would be more likely a perforating or a Volkmann's canal. There's a nice Volkmann's here, look at that. Isn't that cool? I hadn't seen that before. So yeah, we've got our endosteum, we've got our blood vessels within this region here, but we can actually see that really nice sort of perforation that's taking place. And you'd have your Haversian canals branching off these in this way as well. And you can see all these blood vessels here. All right, I can see we're running out of time. We've only got a few minutes left. So again, this is another section. I think we might skip past it. This one's in H&E. So of course, as I mentioned before, the region where we find most of our compact bone is the diaphysis, which is the shaft of the bone in long bones. So this is our compact bone in H&E here. So here's our osteocytes sitting within lacunae. These are going to be parts of our Haversian canals and perforating canals and so on. Look at this line of cells. Look at that. I'm glad we clicked on this. These are our osteoblasts. So our osteoblasts, this is the endosteum. This is the outer fibrous layer of the periosteum, and then the endosteum's on the inside. And all of these cells are the osteoblasts. They look so cool, all lined up. I don't know if we'll see any osteoclasts. We'll sort of zoom around. Sometimes we can see them on the surface there, but not always. So when we're looking for osteoclasts, what we're looking for are cells like this with multiple nuclei, and you can see this depression. This is known as a Hauschip's lacuna. Now, Hauschip's lacuna is a little depression that a osteoclast forms. It forms this sort of actin sealing zone, and then it spews out lots and lots of hydrochloric acid in the form of hydrogen chloride ions plus enzymes, and they can resorb that bone matrix. So they're stimulated by parathyroid hormone, which is a hormone released by the parathyroid glands adjacent to the thyroid gland, and they stimulate the action of the osteoclast to break down the bone, release calcium, and increase blood calcium levels. Yeah, so that's what we're sort of looking at here. These big cells, these sort of depressions, are these osteoclasts making sort of digestions on the surface there. And there doesn't seem to be a lot on this side. I just want to quickly, so this is a mature bone. Again, we've got that junction between the articular cartilage on the left here and the, we have this sort of three-band sort of colour here. So here's our articular cartilage. This line here is sometimes referred to as the cement line. It represents the junction between the normal articular cartilage and the mineralized cartilage, and then we actually have the spongy bone out here. So this line is sort of delineation between the hyaline cartilage, mineralized cartilage, and then this very acidophilic tissue out here is the bone matrix of the spongy bone. So these are the bony spicules. You can see sometimes the orientation of the lamellae here. These are nice here, look at this. These lines forming here. So here's our osteocytes within their lacunae. On the surface we have our endosteum with our osteoblasts and osteoclasts and osteoprogenitor cells. Again, you may need to do a little bit of searching around to get a nice section of that. You can see some of them out of plane of section. But again, there's no blood vessels within the spongy bone. They're all on the periphery. Diffusion is working through these osteocytes, forming those canaliculi, those cytoplasmic processes and so on. All right, well, pretty much hopefully covered the cartilage, histology of cartilage, the histology of bone. We didn't spend a lot of time looking at bone growth. We can probably do that in a future live stream, but that pretty much ends it for the histology of bone and cartilage. Unless someone has some specific questions, I do need to move on to beginning our look at the histology of the liver, gallbladder and pancreas. So I hope you found that aspect helpful. Any questions about the histology of cartilage or bone? It's all very quiet in the chat there. Everyone's just sort of simply sitting back and watching me jabber on. I've been talking a lot. So we've got about another hour of jabbering on, where we're going to have a look at the histology of liver, gallbladder and cartilage. Thanks, Infinite Lives. Thank you, Dr. Shio. As I say, I am going to continue on having a look at the liver, the gallbladder and pancreas, so you're more than welcome to stick around. This is, as I mentioned, more for our first year medical students who've just done the histology of those regions. We're now going to sort of finish up, and look at that, we can leave you with a lovely love heart, because we love histology, don't we? Please stick around. We'll begin our look at the histology of liver, gallbladder and pancreas in about 2 minutes. So we might take a short break and we'll be back in 2 minutes.